want to introduce you to our tutor, Ivana Milutinovic. She is a teaching associate at the Faculty of Sciences, University of Novi Sad, and she will hold a comparing GNN approaches for molecule identification tutorial. Enjoy. We can't hear you, Ivana. You need to unmute yourself.
Okay, sorry. Okay, do you hear me now? I'm sorry.
Yes.
Okay, thank you very much. I'm sorry once again. So, hello everyone. My name is Ivana Milutinovic, and now I will present my research work that I have done for my master's thesis. So, we will start with my presentation. Just a second to share my screen. So, screen, okay, share screen. Okay, does everyone see my screen? Yes. I hope. Yeah, okay, thank you for the feedback. Okay, the title is comparing GNN approaches for molecule identification. And as I said, my name is Ivana Milutinovic, and I'm teaching associate at the University of Novi Sad, Faculty of Sciences. So first of all, I want to tell a little bit more about myself. I have a master's degree in artificial intelligence, and I'm currently enrolled in the first year of my PhD studies at the same university. And also I'm working, as I said, as a teaching associate, soon hope to be the teaching assistant and the same institutions. My field of interest are machine learning and deep learning, graph neural network, bioinformatics and computational biology, and medical data analysis. So feel free to contact me at any time via my LinkedIn profile or via my email. So I think that my internet speed already starting to cause some troubles for me, because I think it may be something here, and I will turn my camera off so we can continue normally without some interruptions. So thank you. See you soon. Okay, we can now continue with the presentation. Like, first of all, we will start with the introduction and motivation for my work. So the analysis of molecules in biological processes plays a crucial role in understanding their biological activity and predicting their impact on various biological systems. However, these traditional methods often fall short when it comes to accurately identifying these activities. And then conventional approaches primarily rely on heuristics methods and manual inspection of molecular structures, which usually involves some basic calculations and limited chemical parameters. While these methods have been widely used, they often struggle to capture the complexity of molecular behavior and interactions. So, these traditional approaches tend to be inefficient for addressing the vast diversity and intricate nature of chemical structures. As a result, they may not provide the necessary precision and scalability required for more advanced applications, such as drug discovery or disease biomarkers identification. So this highlights the need for more sophisticated techniques that can actually handle this complexity effectively. So recent developments in machine learning, especially graph neural networks, have revolutionized the way we approach the analysis of molecular data. So these techniques allow for the transformation of molecular structures into graph-based representations, and enabling a more understanding of atomic interactions, molecular topology, and the underlying chemical properties of molecules. By using machine learning models to process these graphs, we can significantly enhance the accuracy and efficiency of predictions related to the biological activity of molecules. So the application, sorry, I just, okay, speed up a little bit. The application of these advanced techniques allow us to perform deeper analysis of molecular structures, capturing complex relationships between atoms and bonds, and predict biological activity more effectively, facilitating drug discovery, biomarker identification, as I said, and other applications in computational biology and bioinformatics. So, the idea behind this work is to model molecular structures as graph and apply graph neural network to predict their biological activity. The work can be broken down into these following steps. So first of all, modeling molecules into graph structure. As I said, these steps involves representing molecules as graph, where atoms are nodes and chemical bonds are edges, capturing the underlying molecular structure. Then applying graph neural network for predictions, where graph neural networks often used to predict the biological activity of the molecule based on their graph representation, and at the end analyzing and comparing the obtained result, which could say to us the effectiveness of the model, with the focus on the model's ability to handle molecular complexity. So this work utilizes supervised learning, where each molecule is labeled based on its biological activity. The goal is to train a model capable of predicting these activities based on the graph structure of the molecules. Okay. Okay, now we will continue with the methodology which we applied. So we have first of all to introduce some biological background. So since the IOP framework plays a crucial role, which means adverse outcome pathway, in understanding how molecular interactions lead to harmful effects on biological systems. So it connects molecular initiation events through a series of intermediate steps referred to key events, ultimately resulting in the adverse outcome, like chronic effects, some chronic effects, some lethal effects. You know, this structured approach helps in mapping the mechanisms through which chemicals can influence biological functions. For this particular work, the identification of Mias and keys is especially important, as it allows for a more accurate prediction of how chemical impact the female reproductive system. By reorganizing the molecular targets involved in this pathway, we can better understand the underlying molecular mechanism and predict potential toxicology effects. So, for the database used in this study, we relied on the data related to molecules that were tested in the context of the adverse outcome pathway, titled Reduction of Aromatase Impairing Female Fertility. The data set was sourced from the Comtox dashboard, which provides comprehensive toxicological data and information related to the environmental and health impacts of chemicals. In addition to molecular data, the dataset also contains information on the biological activity of the molecules tested in these studies. So this includes activity result across 17 different target tests, all of which are linked to three primarily biological targets, which we previously mentioned. So the dataset compresses data on approximately 11,630 molecules, providing a rich source of information for analyzing the potential effects of chemical on the female reproductive system. Yes, the large number of molecules uh, and the breadth of biological tests in the dataset, making ideal resource for applying advanced analytical methods such as machine learning and graph neural networks to predict by biological activity based on graph molecule structure. Yes. So, uh, pre-processing the data was done in some three steps. Like first, we address the missing molecular information by supplementing and correcting the data through the use of ChemID plus API beta database. This allowed us to fill in any gaps in the molecular data that were not initially available, ensuring the data set was complete and accurate for analysis. So from this data set, the three main types of information are crucial, like molecule name, the SMILES representation, which is simplified molecular input line entry string, which we have an example of on that image below, which is not notation that encode the structure of molecules into a line of text. Like you see that you have some array of combination of some characters or some letters, and also some numbers which represent like molecule structure. Okay, and this SMILES representation is a low efficient storage and processing of molecular information. And the third information that is needed is activity in biological assays, like test. And we have three classes of activity: inactive, like partially active, and active. Okay. As I said, for supplement and correct missing molecular information that was not initially available, we use ChemID plus API beta database. So the collected molecules are composed of 53 different chemical elements, atoms, and four different types of chemical bonds, like single, double, triple, and aromatic one, which is where the strongest one is aromatic and the weakest one between atoms is the single type bond. So uh, based on the SMILES representation, each molecule was modeled as graphs, where atoms are represented as nodes, which correspond to the letters in the SMILES, and bonds are represented as edges corresponding to a specific symbol in the SMILE. So as you see at the picture below, we have some molecule which is partially active, and which is consisted of carbon atoms and I think maybe oxygen atoms and azote atoms also. And there are a few types of like bonds, like we have S for single bonds and A letter for aromatic bond. Okay. The node features. So since in the we and encountered the challenge of missing rich feature representation for the atoms node. To overcome this, we use deep walk and word-to-vec techniques to generate initial vector representation for the nodes. So these techniques are widely used for learning node embeddings in graphs by capturing the structural properties and relationships between nodes. Okay. So we tested little bit, and we came to the conclusion that for each molecular graph, we should create 150 random walks, each with a length of 35 steps in order to cover all the nodes in no matter how huge a graph is in a way of the number of nodes. Yes. So these random walks serve as an input sequence for the word-to-vec model, which then learns to map each graph node atom to a 64-dimensional embedding. So the embedding represents the structural context of each atom in the graph. And to enhance the node features, the embedding for each node is combined with the one-hot encoded atomic labels, which represent the chemical elements of the atoms, as I previously mentioned. So this one-hot encoding creates a 52-dimensional vector for each node, corresponding to the 53 possible chemical elements in our whole data set. Right. As a result, in the end, each node embedding has a total size of 117 dimensions, consisting of 64-dimensional embedding, which is obtained from the word-to-vec model, and the 43-dimensional atomic label encoding. Okay, so, but we have a challenge in data imbalance, because with the majority of like molecules being classified as inactive in biological processes. So this imbalance like pose a challenge for training accurate machine learning models. Yes. So because for us it's more important to have molecules which are maybe partially active or active, because that is more significant to us to detect correctly than to detect these inactive ones. So to address this issue, a data augmentation technique was applied, specifically designed to enhance the representation of molecules from the minority classes. Uh, the augmentation process itself was based on the creation of isomorphic graphs through node permutations. Like isomorphism in graph theory refers to the concept where two graphs are structurally identical through their node labels, or indices may differ. So in our case, node indices were randomly rearranged, and then our adjacency matrix was updated accordingly to reflect these changes, ensuring the molecular structure remained the same, but the representation was altered. So this process allows us to generate new molecular graphs while preserving the original chemical structures and relationship between atoms, which is really important, because we cannot just randomly move atom from another to change the type of the bond, because we have to preserve the chemical validity, yes, of the molecule itself. So the result of this augmentation process was a data set of 20,884 graphs based molecules with the class distributions as stated below, which we still have The most of the molecules which belongs to inactive class, which is labeled like numerically 0. Around 700 belong to the partially active class, 1 numerically, and 6,650 around belong to the active class, numerically 2. Okay. So the models that we used uh, are these that I stated here. Like first of all, there is a graph convolutional neural network, which is a very popular approach in graph-based learning that performs two essential operations in each layer: aggregation and combination. In the aggregation step, the feature of neighbors nodes are collected, and in the combination step, the node's own feature is combined with the aggregated feature from its neighbors. The second model was graph sage, graph sample and aggregation, right? Which improves upon the traditional GCN by incorporating neighbor sampling during training. So instead of using all neighbors for aggregation, Graph Sage samples a fixed size set of neighbors for each node, making it scalable to large graphs. The key steps in graph search are neighbor sampling, aggregation, and combination. So, when the aggregation steps combine feature from sample neighbor using various functions like mean, sum on LSTM based aggregators. Graph attention network introduce some kind of attention mechanism to graph-based learning, which allows the model to assign different weights to neighbors during the aggregation process, depending on the importance of each neighbor's feature. By automatically learning these attention weights, GITs can focus more on relevant neighbors, enhancing their ability to capture complex graph relationships. So this makes GITs like highly effective, especially when the graph structure is sparse or contains nosy information. So, and the last one was graph isomorphism network, which is a model to designed to address a key limitation of traditional graph neural networks: the ability to distinguish between graphs with different structures. Uh, GIN includes powerful aggregation methods that enable it to distinguish between graphs that are structurally different, even when their edge relationship are equivalent. These features make this model particularly useful in tasks where graph distinction is like critical, such as graph classification in scenarios where small structure changes can significantly affect the graph properties. Uh, when we talk about hyperparameters, to optimize the performance of all dimensions models, the Optuna library was used for hyperparameter optimization through automatic tuning. Like Optuna is a very efficient and flexible framework that automatically search for the best combination of hyperparameters and based on the specific data set or on the specific problem, and ensuring that the models are trained with optimal settings for improved performance. Like by exploring different hyperparameters configurations, Optuna helps to identify the best performing model for the molecular activity prediction task. So the image below is representing like one flow of the model that we use, like for our input. we have like a few layers of graph convolutions, then apply some kind of pooling, like sum pooling, average pooling, max pooling case, add some regularization like batch normalization, dropout, and at the end we have some linear classifier to tell us which is the probability for some molecules to belong to some of mentioned three classes like inactive, partially active, and active one. Okay, the chaining process itself was consistent initially of stratified splitting data into training a test set with native 20 ratio, and the training set was further split into training and validation set in the same ratio. Like then class labels were converted to the one-hot format to enable multi-class classification. So batches and other hyperparameters were defined based on the result of the hyperparameter optimization process. So several callbacks were added to improve the training process itself, like learning rate scheduler, which help adjust the learning rate during training to optimize convergence. Early stop, which stop the training if the validation loss does not improve, preventing overfitting, right? And the F1 score callback, which tracks the F score during training to help monitor the model's balance between precision and recall, because we do not want to have like really high accuracy value, because then we wouldn't be sure if it's reason for that because model classified correctly like all instances from the three classes, or just always pick like majority class, like the class that in of inactive molecules. So the training process run for up to 50 epochs on a GPU supported cluster, which we have at our faculty. So in that way, we ensured efficient model training, and later on we will see how one job script looks like to run such a program on the cluster. Okay. Results. Uh, First of all, here are some like graphs which are related to training metrics values for graph sage model, because he was the quickest and required the fewest epochs. So we see that we have a loss function which is categorical cross entropy, right? We have average precision, and we have F1 score, and also raw calc through the epoch. So we see that loss is all right. Actually, it has some like monotone trend. Later on, for Refiadon score, we see that the curve of validation is a little bit nervous, and it's not stable until like 16, 17, I don't know, epoch, you know. And for raw calc, we see that the validation curve is below the training curve for around 0.01 or 0.02. Okay. So the result of evaluation was performed using several metrics, which I stated previous, like loss, which is categorical cross entropy, softmax, uh, accuracy, which indicates the overall percentage of corrected predictions. F1 score, a metric that balances precision and recall. ROCAUG, the area under the receiver operating characteristic curve, which evaluates the model's classification performance. And average precisions measure the precision recall trade-off. Like in the here in the table, we see that Graph Sage model has the best result, which means that he outperformed the other models across all evaluation metrics. So it's not quite like a big difference, but we see that the training process is like stable. We do not have high standard deviation, and still across the all metrics, Graph Sage proven to be the best one. So I think before we go to ideas for future work, we will take a look in my Colab notebook. I think that you have like access to this notebook. Okay, here it is. I send the link to my GitHub to my GitHub repository, which all materials are here, so you can download it later on, look later. Now you can look with me. Okay, first of all, we need some libraries to import, to install, like TensorFlow, Spectral, RDKit, okay, and to import all the others like NumPy, OS, H5, Pi, and Random. Okay, first of all, I will clone my Git repository because here are my folders with data. So we will not here demonstrate the whole process, like to work with the whole data, just for some examples of them. First of all, in the data folder, we have a CVs file, which are related to the test, to the essays, which said if some molecules in that files are up or down, which means that they are active or not active. So we have to first process data on various biochemical test assays and their result, combining them into several data frames. So it also prepares data on small strings, like we discussed, and remove duplicates. In the end, we obtain a list of data frames and consolidate the data frame with small data. Okay, from the essays, from the CV file, we use like preferred name, like hits, which is a column that refers to activity, to the kind of molecule activity, and also we done. I didn't put that here. As I said, we needed to fix some data, missing data, with ChemID EpiPlus, but EpiPlus beta database. So we need to have all smiles presented, like for all molecules that we have in these CSV files. To none of them needs to be null. Like every smiles needs to have data. Okay. For example, for one essay, we have like 440 molecules that are inactive, like zero label, and 58 of them which are partially active. So how we convert small string to graph representation. This is method for that. When we first use chem class from RDKit library, when we get molecule from small strings and create a network X graph, where we set which label does this molecule belongs, and we have bond type mapping for single bond. There it is numerically 1, for double 2, triple 3, aromatic 4. Then we come to iteration through the atoms of like molecules. When we get ID, get symbol, and the degree of that atom, and add a node to our network X graph. And then we have a bond. We get the bond type. We set that bond type numerically. Okay. Now we get a graph like from one row in our essay. So I just use here one graph, not all, because I just want to demonstrate how does that look. Okay. We have smiles in a row. We have label. We have like active, inactive, partially active. Like if the molecule label is 2, then the molecule is active. Otherwise, if it's 0, it's inactive. If it's 1, it's partially active. Okay. Then we get smiles from the row of the file, and we check if the smile is not none. It shouldn't be none. And then we call these method smiles to graph, and we pass smile string and label, which is active, like kind active, partially active, as I said, and then add that graph to list of graphs, which we here stated before. Okay. Then we want to do the visualization of the like molecule graph that we created from small strings, and we have like matplotlib library used here, and like color nodes and color edges, and write on the graph which was the bond type, like you said on the you have seen on the presentation, when we have S for single type of bond, like A for like aromatic type of bond, etc. Okay. Now we can see we just want to access this one, like take only one molecule from the essay, and then we will see that it is partially active, and it smiles for some molecule which name is tetrahydrocurcumin. I don't know how to pronounce that, and we have smiles for that molecule, and this is the its graph representation. Like you see, we have, I think, as I do recall, that the char equally is a stator for double like bond type. You know, when you have like these kind of bracelets, like it is said that you have some circle in your molecule, etc. I just try to remember these specifics, like what does any character exactly means in the small strings. Okay. But now we have some carbons, we have some carbon atoms, we have oxygen atoms, and I think that's all. And if we look at smart string, we also see that uh, these molecules is consisted of only two chemical elements, as I may say. Okay. We talked about generate random walks and node embedding, since we only have information about the label of atom and these type of bonds, and we generate one walk for molecule graph, one walk for molecule graph. When we if the node does not have neighbors, we then stop the walk. Okay, and we use some random choose of node from which we will start the walk. So the next is to generate random walks, like more of them. I think that we said like 150, and then we call the like method which generate only one random walk, and we then put it in our list of walks for specific graph of the length of the 35. And then we apply, when we generate this walk, we apply the work to back model, where the input is walks, and this model generates for us the embedding for every node in every graph that we have. And also, when we generate that 64-dimensional embedding, we add to them like a 43-dimensional vector, which refers to which element, which chemical element that node represent, like carbon, oxygen, I don't know. Okay. Sorry. Then, okay, here we stated all the elements that can occur in any molecule through all the data that we have, and we give them some index according to their position in this list, like because when you have one hot encoding for these elements, then we have, like, if you have 53 elements, the vector is consisted of all zeros with only one value that is 1, which represent which element is for that node. Okay. Then I have again like classes like 0, 1, and 2, and then when I read graph from GML file, then we extract information like adjacency matrix and label, and then do data augmentation using graph isomorphism for graphs that belong to the minority class of activity, like I said, like partially activity and active. And it is some kind of oversampling using replication on the graph, but with modified adjacency matrix, because we changed the node indices. Like we just not make a replica of every molecule that belongs to minority class. We just switch indexes, so this change reflect on the matrix. Okay. And this is the method for that. When we load like this from GNN file, like this, which we saw above, like this molecule, which is partially active because we have 1.0, which means which class these molecules belong, to which class these molecule belongs. And when we load it, we first always check if all degrees, if all node degrees in nodes are greater or equal than 1. Why is that? Because in some like molecular structures, you do not have like atoms, nodes that is not connected to any other nut or in any other atom, to the any other atoms. You always need to have for one node at least one neighbor, one atom that is connected to that node in order to stay like biologically valid, chemically valid. Okay. Then we append that graph to the list and append the label and append the original matrix. So then we check if this label is active or partially active, because we want to do replication for the molecules that belongs to the minority classes. Okay, and then we just random shuffle nodes in order to get new like indexes for them and to create like new matrix adjacency, which will like mix the rows and columns, which will be different than the original matrix. And I think we have to do this for like 4 or 5 times, because in original dataset, sorry, because in original dataset we have around 11,630 molecules, but like around 7,500 of them belongs to class of the inactive molecules. So very small amount of data of molecules belong to the class active or partially active. So we have to replicate them as much as we can, so we can try to accomplish like similar numbers of molecules belonging to each class. So then we like sorry. So we like use the same label for that molecule which we got from these random mixing node indices and like indexes, sorry. So then we use that name again. So it's not like copying paste the same like molecule. We somehow change their not structure but maybe representation of their structure, which is important for the graph neural network models. Okay. Then we generate these embeddings. Then we combine these embeddings with atom labels, with which element every node is a part of, like oxygen and that. And we say that we get graphs which are class of network X graphs. And after we created node features embedding, graph embeddings, we store them together with matrix, graph label, and name into H5 file, because we try to save these data in some other ways, but it was very like slow, like inefficient, and we decided to store it like in this kind of format. When we create some like group which represents graph, we have X for embedding of that graph, we have A for the matrix, and we can see that example of some feature vector when we have for every node, like this is like one node, okay, we have some numbers, which is first embedding that we got by generating from word to vec model, and then we add like 53 the dimensional embedding, which refers to atom element, like element of the atom that node represents. And we see that the shape of node feature vector is like like some tuple 27 and that means that we have in that molecule 27 nodes, 27 atoms, and we have for every atom like embedding with a dimension of 170. Okay, and we have example of matrix, like we see that we have like weighted matrix because we encoded the bond to be like numerically, like to reflect the like strongness of the bond itself, because the 4 is for the strongest one, which is aromatic, the 1 is for the weakest one, which is single, etc. Okay, and the shape of like matrix is 27, 27 for every node, right? So we see the total number of saved graphs is 5. Why is that? Because initially we have only one graph, because we replicated it for 4 times, and now we do not have only one graph. We made like 4 more of them, in order to fight, to overcome this data imbalance that originally came. Okay, now when we like save our graphs to the file, we create the spectral data set of spectral graphs, which we will use as a input for our GNS. Okay, GNNs, sorry. So okay, we read from file, like we get one graph group, we get node features, list of node features, like node embeddings for every graph, we get matrix, we get what like molecule name is, and we get like like which label these molecule belongs to. Okay, and we create then a new graph with embedding matrix, adjacency matrix, and molecule name, and we add then graphs and labels to the list of graphs and labels. Okay, it is important when we wait a second, like okay, we have now see that we have spectral graph, that we have like a shape of the embedding, which we already saw, and the label for this graph is one, which is partially active. Okay, now we can see how our models looks like. We have 4 of them, like GCN, like Graph Sage, GIN, and GAN. Sorry. When we have, for example, for GCN, we have 3 convolutional layers. We have a ReLU activation function. We have global max pooling. We have dropout at some rate. I do not remember. I think that it is 0.2 drop rate. And we have 2 dense layers in order to, at the end, we put one more dense layer which will have activation softmax function, which will give us the probability of for each molecules for belonging to each class. Okay. sorry. For graph stage, we have some similar similar situation. Like aggregate principle is like mean aggregation. We have some batch normalization and also flatten. But here are some difference than the previous model. Like you see, we only have for inputs two variables. We have x, which is node embeddings, and we have a, which is adjacency matrix. But for graph sage model and for GIN model, we have third parameters, third like value, which is I, which represent the index of node, so we can connect them to its graph. What does that mean? So when we want to train like graph sage model, we then have like this joint batch loader. This is from the spectral library, and he used like multiple graphs, combining them together in one really big embedding. It's not just if we have 5 graphs, we do not have 5 embeddings, 5 different embeddings. We only have one big embedding. Because he trains with like how to say that, like combining these graphs together in one big embedding. So we need to have like I index, which represent for every node in that big embedding to which graph originally it belongs. Okay. And also we have to have like a sparse matrix, because for these models, graph sage and GIN, they do not accept input for matrix in like original format. They want only to store places in the matrix which are not zero. Like it's for them, it's like sparse matrix. Okay, because for them it's too much of zeros potentially can be in one matrix. Okay. Then we have GIT model, when we where we have two convolution layers. We have batch normalization. Okay, we have we first apply convolution layer, then batch normalization, then dropout, then second convolution layer, batch normalization, dropout, then pooling, and we have like like dense layers at the end. Okay, and same for the like GIN. Okay. So the training process is like for any other model, I would say. Like we had to split our data on the train and test initially, and after the train test, we had to split stratify, like stratify, to have same distributions of classes in all the split tests sets. Sorry. And then we split our train set into train and validation, where we have like very in a train we have like 3 graphs. In validation in test only 1, because we worked with just 5 graphs. Okay, we have number labels of labels, which is 3, and we convert our labels to one hot format, which we'll see that for epsilon train shape it is 3, 3, we have 3 graphs, and for each one of them a label is represented as 3-dimensional vector. Okay, then we from this splitted like data, create dataset, which is a class from spectral data, like module library, you know. And we create again graphs like we used to do when we loaded our graph from the file. Okay, and we have, like I said, like these joint batch loaders create batches of independent graphs by concatenating their features and matrices while keeping their structures separate. So this is useful for efficiency training or on dataset with multiplied unrelated graphs like molecules or networks. Okay. So the batch size was set to 60 as calculated by Optuna, and all the others, like parameters, were set according to Optuna, what it calculated for us. Then we create our model and pass these parameters, value for these parameters. And as I said earlier, we created like various callbacks such as learning rate scheduler, early stopping, and F1 score callback. When we compute F1 score, like this method, I may be passed. No, it's here. Sorry, it's here. Okay. When we calculate F1 score and we create F1 score callback like scheduler and early stop from TensorFlow Keras callbacks, in which we monitor like validation loss. Okay, and we have patient 5 for 5 epochs. Okay. Then we compile our model. We use optimizer Adam for loss like categorical cross entropy and like metrics that we use to monitor if is accuracy, our F1 score, our like curve, and our Rockout curve and average precision. Okay. Then we used like class weights to which adjust like the weights inversely proportional to the class frequency in the training data. So that means that we give more weight to the molecules which belong to like minority classes, which is still present because we do not have like completely balanced like data set. So our minority classes, molecules from these classes still will get like better weight, like higher weight while training. Okay. And each example of code for model train, you can maybe run it at home. Now we won't do any training. We just want to see the result. Like we had the loss epoch function, which will visualize our loss through the training process, accuracy, F1 score, raw calc, and an average precision. Like then we load these data from the GitHub repository, which I stored earlier, and we see for every model how it behaved during the training process. Okay, we have loss, we have accuracy, F1 score, raw calc, and average precision for each of 4 models. So we say for Graph Sage, for example, that raw loss seem pretty good, that it goes low as can, but we see that accuracy and raw calc are really like nervous. It's not stable during training, but on the other hand, F1 score, which is important to us, are pretty much stable during the epochs. Okay, the similar situation we have with the other models. Okay, just to go through all the like visuals and to see at the end that we had the evaluation results for every model, which said that we have like test loss, which is which is not the lowest one. The lowest one is for graph sage, which we saw at the presentation already, and and we have the highest test accuracy, the highest F1 score, and the highest raw calc. I don't know why average precision is not stated here, but here we have it at the last two models here. Okay, so for the end, it will us to comment the classification report for our models, which is like, it's not like confusion matrix, but similar when we see per classes how precision and recall which value these metrics like have. So we see that, for example, for GCN, the model performs really well on class 0 with high precision and recall, but really struggles with class 1, especially in recall, because it's only 16%, meaning it misses many true class 1 instances. So the model has a moderate performance, like on the class 2, with like balanced F score 0.60, but the overall accuracy is 62%, but the class imbalance with class 0 being dominant is evident, as the model is biased toward class 0. Okay, since we done data augmentation, and we have like similar number of instances per every class, like it was different for like 100, 200 nodes, you know, but it's not enough, because we do not have some variety molecules, like some various molecules. In the original data set, we have like 7,500 different molecules belonging to class 0, which refers to inactive class. But when we do that replication, we do not get like new molecules. It's still the same molecules, but from some models, it may seem like it's different, but it's actually not, because we just mixed our matrix. Okay, so it still has struggles. All the models have struggles to identify molecules which belongs to these classes, which initially were minority. Okay, so what are the conclusions and some idea for our future work? Is that first of all, we like increasing the number of feature for each node in the graph, which means that we want real, like natural physical chemical properties of atoms and molecule. We think this could be done, yes, by adding detailed information about atoms, bond, like molecule topology, molecule structure, and by doing so, the model probably would have richer input data, potentially leading to better understanding and prediction capabilities. The the second idea is exploring a wider range of data augmentation techniques for molecular graphs, but it's important to assure, anyway, that new augmentation methods retain the biological and chemical validity of the molecules, preserving their characteristics. And this will ensure that augmented data remains useful for training models while maintaining the integrity of the molecular properties. So we cannot, as I said earlier, we cannot just like mix node changes, the bond types change, which atoms are connected to the other, to the some other one, because we are not sure if it is chemically valid, like biologically valid. So it is, according to my opinion, really challenged task. Uh, Also, future research could investigate the use of deeper or more complex graph neural networks architecture. So this might involve combining different GNN models to enhance performances. Hybrid approach could leverage the strengths of each model to capture diverse graph feature and better learn from the data. Like we maybe do not need to have like 4 separate model, yet we can build some like combined model hybrid, as I said, which could maybe provide us better result. And finally, an interesting direction could be to explore methods for directly obtaining like molecular data in graph format, bypassing the need for conversion from other representations. For example, we have here from smiles. So this approach could streamline the process and possibly enhance the accuracy and efficiency of graph-based modeling in molecular research. So at the Chem ID plus SAPI beta database, they have sources of like molecules which are in GML format, in 2D sorry 2D or 3D format, and we can download it. But generally problem with biologically database which have biological chemical data, that they also have a lot of missing data, lot of inconsistent data. So it's on the one hand like good idea to get initially data in graph format, but it's also really challenging because maybe maybe that database contains just few of these data, not too much, and then we will have problem. So conclusion, what I was talking about here, and we covered the demonstration of applying graph neural networks to a problem in the fields of biology and chemistry. The procedure for data acquisition, pre-processing, and augmentation were explained, as well the applied models and the training process. So the results of training and evaluation were presented, and at the very end, ideas for improving the obtained result in future work were outlined. So Thank you for your attention, and feel free to ask any question if you might have one. Just to see where are you meeting. Okay, here I am. I will now turn on my camera just in case. Okay.
We have a few questions sent in the chat. If you could open it for yourself.
Okay. Sorry, I didn't saw that. Thank you. Great work. Okay. Graph to edge to VEC model. Okay. Did you consider bias optimization for? Okay. Parallel instead. How do models handle error in data such incorrect smile and coding? Okay. As a non-specific example, does not permutation preserve chemical majority portion? Okay, thank you for your questions. First of all, I will go step by step. Okay, we didn't try a graph to vec graph to vec model because it is for me like a first kind of research work, and it was like preparation for the next steps of my research during my PhD. So we tried like what came to our mind at first, and it gave us a really good result, which we want to improve since I will continue do the work on on this topic which I was talking about. So, did you consider Bayesian optimization for hyperparameters in parallel or instead of for tuna? No, we did not actually, because we at first tried like like to do that manually, but then I talked with my colleague and others, and they suggested me to try like Optuna library, and to in order to get like more precise result, more better result that I had it initially. So it is a thank you for me. This is a really good question because it gives me some idea in which direction I should go with my research and to try new methods. How the models handle errors in data? The models do not have errors like in data, because when we pre-process the data, we ensure that we do not have we do not have like data which is incorrect. Like we earlier like check if all the nodes have like degree at least one, because this is the first first step to have like consistent or like chemically valid data. So when we come to train the model, we do not have error in smiles or activity labels missing. We done good pre-processing and ensure that does not come to the case. Examiner does not. Okay. As I said, maybe I was not clear completely. We do not like permutate node. We just permutate like indices of the node. When we have like three nodes, 0, 1, 2, and 0 and 1 are connected, 2 and 1 are connected. Okay, and then we like mix like change like replace with another indices. Then my old node that was 0 index now became 1 index at index 1. Okay, my node that previous was index 1, he is now in index 2. Okay, and the second one that previous was like the index 2, he is now index, I don't know, 0, as I said. And that change reflects on the matrix there, directly. So we do not permutate node in like chemical way, like we change which type of bond are atoms connected by, or we maybe do not change like if carbon is connected to the other carbon by single type of bond, or and we shift that or replace that with some atom of I don't know, oxygen. And no, we do not do that. We just mix like indexes to get like the different representation of matrix. Okay.